Welcome, curious mathematicians, to learn math by example at Sam's Hub. Today, we're soaring into the world of trigonometry, tackling a real world, high stakes challenge that will put your mathematical thinking to the test. Imagine you're piloting a survey drone D high above a perilous alpine region, tasked with mapping a challenging terrain. You've identified two critical ground markers, A and B. From your drone's current position, you measure the angle formed by these markers. Angle ADB at 58 degrees, you also precisely measure the distance to marker A, AD, as 1.2 kilometers. But here's the twist. Dense fog obscures your view to marker B, preventing a direct measurement of distance dB. Instead, a ground team at marker A comes to the rescue, measuring angle DAB at 40 degrees. Your mission, should you choose to accept it, is to calculate the unknown distance dB and the area of the triangular region ADB. And perhaps more importantly, considering the limited information, is there more than one possible shape this triangle could take? This intriguing problem will be our guiding star as we navigate in today's lesson, covering the sine law, the cosine law, the derivation and application of the area of a triangle using the sine rule, and the fascinating concept of the ambiguous case. So let's dive in. First up, the sine law. This powerful tool helps us solve for unknown sides or angles in non-right angled triangles when we have certain combinations of information. Consider an triangle ABC with sides A, B, and C opposite to angles capital A, capital B, and capital C respectively. The sine law states that the ratio of a side to the sine of its opposite angle is constant for all three sides and angles in that triangle. That's A over sine A is equal to B over sine B equals to C over sine C. We typically use the sine law when we know two angles and any one side, often called ASA or AAS, or two sides and an angle not included between them, which is SSA. Now we'll explore the implications of SSA shortly with the ambiguous case. Let's see an example. Suppose we have triangle PQR, where angle P is 60 degrees, angle Q is 40 degrees, and side P, opposite to the angle P, is 10 centimeters. We want to find side Q, opposite to angle Q. Using the sine law, we set up the ratio 10 over sine 60 is equal to Q over sine 40. To find Q, we simply multiply now 10 by sine 40 divided by sine 60. This gives us approximately 7.42 centimeters. Simple, right? Next, we have the cosine law, a generalized version of the Pythagorean theorem applicable to all angles. We use it when the sine law isn't enough, especially when we know either two sides and the included angle, known as SAS, or all three sides, SSS. The cosine law states A squared is equal to B squared plus C squared minus 2BC cosine A. Similarly, B squared is equal to A squared plus C squared minus 2AC cosine B. And C squared is equal to A squared plus B squared minus 2AB cosine C. Now notice the pattern here. The side you're solving for, squared, is equal to the sum of the squares of the other two sides, minus 2 times the product of those two sides multiplied by the cosine of the angle opposite to the side you're looking for. For example, in triangle XYZ, suppose side X is 8 centimeters, side Y is 12 centimeters, and the included angle Z is 75 degrees. Now we want to find side small z. Substituting our values into the formula, we get z squared is equal to 8 squared plus 12 squared minus 2 times 8 times 12 times cosine 75. This simplifies to z squared is equal to 64 plus 144 minus 192 times cosine 75. Calculating this out, we get z squared approximately 158.3. Taking the square root, z is approximately 12.58 centimeters. You can also rearrange this formula to solve for an unknown angle if you know all three sides. For instance, cosine A is equal to b squared plus c squared minus a squared divided by 2bc. For example, in triangle XYZ, suppose side x is 8 centimeters, y is 12 centimeters, and z is 15 centimeters. To find angle z, substituting our values into the formula, we get cosine z is equal to 8 squared plus 12 squared minus 15 squared, all divided by 2 times 8 times 12. This simplifies to cosine z equal to 64 plus 144 minus 225 divided by 192. Applying the inverse function of cosine, we get z equal to cosine inverse of minus 17 over 192, which is 95.079715, etc. degrees. So z is approximately 95.1 degrees rounded to 3 significant figures. Before we talk about the area of any triangle, let's briefly revisit the fundamental area formula for a triangle and then see how it leads to a more general form. We all know that the standard formula is the area is equal to half base times height. Consider triangle ABC now. Let's draw the height h from the vertex C down to side AB. If we consider side AB as our base, let's call it small b, then the area is simply 1/2 times b times h. Now look at the right angle triangle formed by the height, say triangle ADC. We can express h in terms of angle A and side AC, which we'll call C. Specifically, the sine of angle A is the opposite side h divided by the hypotenuse small c. So sine A is equal to h over c. Rearranging this, we find that h is equal to c times sine A. If we substitute this expression for h back into our original formula, we get the area is equal to half b times c sine A, which simplifies to half bc sine A. And this is a very powerful general formula that we will use later on. The derivation we just performed gives us the general formula for the area of any triangle using the sine rule, even if that triangle doesn't contain the height. The area of a triangle is equal to half the product of two sides and the sine of the angle included between them. And remember, the angle should be included between them. So for triangle ABC, we have three versions. The area is equal to half BC sine A, or half AB sine C, or half AC sine B. The key requirement here is that you need to know two sides and the angle between those two sides. Remember, between is the meaning of included. So when we say the angle included, it means the angle between the given sides. This is often referred to as the side angle side, or SAS condition. Now let's quickly apply this. Imagine triangle DEF, where side D is 7 centimeters, side E is 10 centimeters, and the included angle F is 65 degrees. Using the formula, the area is equal to half times 7 times 10 times sine of 65 degrees. This simplifies to 35 times sine 65. Calculating this, we find that the area is 31.72077, etc., which is approximately 31.7 centimeters squared. This formula is extremely useful when you don't have the perpendicular height readily available. Now, let's explore a very important concept in trigonometry, particularly when using the sine law, the ambiguous case. This occurs when you are given two sides and a non-included angle, specifically an angle and the side opposite to it, plus another side. This is the SSA case, side-side angle. When does it get ambiguous? Now it depends on the length of the side opposite to the given angle, relative to the other given side, and the height. Our first step is always to calculate the height h from the vertex opposite to the given angle to the side adjacent to it, which is AD, where D is the intersection point between AB and the height. Now this height is always equal to B sine A, since we have a right triangle, ADC. Now, to understand the ambiguous case, think of it like this. A is the radius of a circle with center C. So, there are four main possibilities now. 1. If the side opposite the given angle, which is the radius A, is shorter than the height h, then the circle doesn't intersect with AD, so no triangle can be formed at all. The side isn't long enough to reach the base. In the second case, if side A is exactly equal to the altitude h, and altitude here means the height, then AD is tangent to the circle, and we form precisely one right angle triangle, so B and D are on top of each other. Case 3, this is the ambiguous part. Now if side A is longer than the height h, but shorter than the other given side B, then the circle intersects AD at two distinct points, so two distinct triangles can be formed. One will be the acute angled and the other will be the obtuse angled, using a supplementary angle for the second possible solution, which means when you find the first angle, let's say B1, using the sine law, you can find the second angle, let's call it B2, using 180 minus B1. And 4, if side A is longer than or equal to side B, there is only one possible triangle, since the circle will intersect AD at exactly one point, B. Now let's consider an example for the ambiguous case. Say we have angle A as 30 degrees, side A is 6 centimeters, and side B is 10 centimeters. Let's first calculate the height h. That will be 10 times sine 30, which is 5 centimeters. Now let's compare. A is 6, h is 5, B is 10. So we have 5 is smaller than 6, which is smaller than 10. So we have two possible triangles. You'll find two possible values for the angle opposite to side B, one acute and one its supplement. This is critical for solving our drawn problem. Alright, now it's time to put everything we've learned into practice and conquer our Alpine Mapping challenge. Recall our problem. We had a drawn D, angle ADB 58 degrees, distance AD 1.2 kilometers, and angle DAB 40 degrees. We need to find DB and the area of triangle ADB. First, let's find the third angle, angle ABD. Since the sum of angles in a triangle is 180 degrees, then angle ABD will be 180 minus 58 minus 40, which gives us 82 degrees. Now, to find the distance DB, we can use the sine law. We have a known pair, AD and its opposite angle, 82 degrees. We want DB, and we know its opposite angle, 40 degrees. So, DB over sine 40 is equal to 1.2 over sine 82. Solving for DB, we get 1.2 times sine 40 divided by sine 82. This calculates to approximately 0.779 kilometers, rounded to three significant figures. Okay, great. Now, one part of the mission is completed. Next, the area of the triangle region ADB. We now have two sides AD and DB and the included angle ADB, which is 58 degrees. This is perfect for our area formula. Area is equal to half AD times DB times the sine of angle ADB. So half times 1.2 times 0.778925 times sine 58 degrees. Remember, we used the full answer from the previous question, which is dB. This gives us an area of approximately 0.396 kilometers squared. Mission accomplished. Finally, the crucial question. Is there more than one possible solution for the triangle's shape, indicating an ambiguous case? Remember, the ambiguous case occurs with side-side angle or SSA. In our problem, we were given angle D, side AD, and angle A. This is an angle side angle scenario or AAS. Since we were not given two sides and an unincluded angle in the initial problem setup, there is no ambiguous case here. There is only one unique triangle that fits the initial measurements. However, if the problem had given us, say, angle A, side DB, and side AD, then we would need to check for ambiguity. For instance, if side DB was shorter than the altitude from D to AB, there might be no triangle, or two triangles, or one triangle. But in our actual problem with angle side angle, the triangle is uniquely defined. Today, we've navigated the powerful tools of triangle trigonometry. We mastered the sine law for when you have angle side pairs and the cosine law as a generalized Pythagorean theorem for side angle side or side 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 scenarios. We explored the elegant derivation and application of the area formula using the sine rule, requiring two sides and their included angle. And critically, we demystified the ambiguous case, understanding when multiple triangles can exist and how to identify them using the height. These concepts are fundamental not just for IB Math success, but for countless real-world applications, from surveying and navigation to engineering and astronomy. If you have questions or want to discuss a problem, share your thoughts in the comments below. Engaging with the material and your peers is a fantastic way to deepen your understanding and analytical skills in mathematics. To check your understanding right now, head over to our website to check the practice quiz. Don't forget to like this video and subscribe for more essential IB Math lessons. Until next time, keep exploring the beauty of mathematics.